Hi, this is Tom McNulty. I'm an initiate at Tau Beta Pi at the University of Illinois Computer Science program. Today I'm going to do a quick walkthrough of the sheeps and wolves problem in Python. You may have heard this as prisoners and guards, but the objective is that you have a certain number of sheep, and wolves on one side of the river, and you need to get them across the river. You have a boat, but you can only take one or two animals at a time. Now, as you're moving the animals, sheep must always be greater or equal to the number of wolves on both sides of the river. And ideally, the selection of moves that you make needs to be the fewest possible moves. So the strategy that I'm going to kind of walk through and show in Python is just more of a generate and test type strategy in which I generate possible moves and then I analyze those moves for their validity. And if they're good, we keep them and move on with them with future moves, and those that are not valid, we discard. So graphically, this is what it would look like. In this representation, you could just assume that the blue people are sheep, the orange ones are wolves. And so this generates all possible moves. We're starting out on the left here with the boat on the left-hand side, and then the next move has the boat moving to the right-hand side, and then these different possibilities. Now, some of these are good, and some of them are not good. The two that have X's on them are those that resulted in like sheep being fewer than the number of wolves. And there are one, and it's like one or more sheep, and there's more wolves. So that's a bad situation. And that's an invalid situation. And so say we kept the valid moves from the first set, we can now generate the next step of sets, or a step of moves. Now those that are in this greenish yellow, these are invalid moves, not because they're violating sheeps versus wolves, it's that they're going back and regenerating a previous state. In this case, it's the initial state. So we don't want to do that. That would be quite inefficient, as we could get caught in loops. So using Python, the data structures that I'm going to use is the possible moves list, all the different, the all possible moves list. And then I have two different queues. One that is going to hold the state, and the state would be, an example would be just this. Any of these, as long as they're valid, that would be a state. And then there's the movements queue, which would be the movements history that generated that state. And then we have a dictionary that captures or holds on to all previous moves so that it's kind of a global move history, and so we don't want to be generating those, and so that those will be just kind of a verification check to see if we have that already, and if we have it, we will discard it. So I've written down my process here. It's kind of graphically represented here as well, but it's initially just start with the initial state, generate the possible moves, evaluate those moves for validity and novelty, and if they're good, we will add them to the state and to the movements history queue and move on from there. And then so looking at the code, what I first want to do, I created a class for this. We have the solve method here, and so initially these first 25, 30 lines are just initializing everything. Initializing the state queue, the movement queue. The initial state is captured in a list. It has 5 digits. The first one is the number of sheep. For the initial state, it's the number of sheep, number of wolves, and that represents the left-hand side of the river. Then the next two represent the right-hand side of the river, and then the last one is the boat. So 0 is for left-hand side, and then 1 is for right-hand side. So the initial state is the converse of the goal state. So you can see that the sheep and wolves both move to the right-hand side of the river, and the boat is on the right-hand side of the river. So we make the current state the initial state, and put that current state in the queue. We then create a dictionary to hold on to all the different states. We then have our movements list, which looks like this, and this just represents, these tuples. The first 0 would be for sheep, the second one would be for number of wolves, and that's the number we're moving. And then the boat direction would determine if that quantity is moving left or right. So now here we start the loop. So as long as we have something in the queue, we're going to keep going. Now, the first step is to pull out the first item from the queue, the state queue, put that in the current state. And then also for the movements, if this is not the initial state, we will have a move history that we will want to pull from the queue and then append the next move to that. Next, we will want to go through each possible move. And so right here, I just have a couple of lines that eliminate bad moves when we have an initial state. And that is simply moving just one animal to the right. There's no other animals on the right, and so that animal is going to have to come back, and so that's just a wasted, inefficient move, so I filter out those immediately. The next is, for generating the next current state, this is when the boat is on the left-hand side, and so we add the movement quantities to the current state, and then this next section is when the boat's on the right-hand side. Once that's done, we check to see if that move is in the history. If it is, we hit continue, which brings us back to the start of the loop, and we'll start over again. Assuming that it's not in the queue, then we can filter out undesirable states where the sheep are less than the number of wolves. And so this chunk of code checks the left-hand side of the river. This chunk checks the right-hand side. If it makes through that, then we apparently have a good move. So we add this to the new state history and to the state queue. This code then just adds the movements to the movement queue. We have different code if it's the movement queue is empty or if we're working with the previous queue. And then at the end, we just check, does the new state equal the goal state? If it does, we return the updated history, which is the movement history. And that's what we can verify to make sure that it is the most efficient. If it's not, if we never actually get to the goal state, we return an empty list. So let me just comment that out. I can run this. And so my code, before I actually get to that, my code checks out many different possibility or permutations of sets of sheep and wolves. So we go anywhere from 1 to 11 sheep, anywhere from 1 to 11 wolves, as long as the sheep are less than or equal to the number of, or excuse me, greater than or equal to the number of wolves, then it's a valid initial set, and then we run that through the system, or through the code. And so we start out, sheep 1, wolves 1, it just takes one movement. Just put them both in the boat, move across, and then we're done. And then, as you can see, we get more and more wolves and sheep. And so the example that I showed graphically, it was 3 sheep, 3 wolves. That process would have taken 11 moves. And in the most extreme cases, it'll take 35 moves when we have 10 wolves, 10 sheep, 9 wolves. And then you might have seen that we have some empty solutions. And so this was not solvable, where sheep are 10 and wolves are 10. So that is the process of generating and testing all valid possibilities and solving the sheep and wolves problem. Thank you very much.